Welcome to the 36th lecture of combinatorics. So, in the last class we were discussing one last theorem about the partitions. So, the theorem was about partitions of a number n whose parts are all different unequal parts. So, among that kind of partitions we have two groups. One is where the number of parts are is odd, the other is number of parts is e. So, we used these two letters E and O to represent these two sets. We showed that for most n E is equal to O, that is for all n positive integers n where n is not equal to omega of s or n is not equal to omega of minus s, where for s equal to 1, 2, 3 up to whatever. And what is this omega of s? Omega of s is equal to 3s square minus s by 2, and omega of minus s is 3s square plus s by 2. Then we showed that if n happens to be of this form or this form for some s, then either this cardinality may be one more than this cardinality, or this cardinality may be one more than this cardinality, and which is bigger is decided by the parity of s. If s is odd, s is an odd number, then this cardinality will be bigger, and if s is an even number, this cardinality will be bigger. We have proved this statement by considering the Ferrer's diagrams of the partitions involved, and then showed a bijection in the first case, this case, and then a bijection between right. In the other case, we removed one special partition from the set in which it is contained, and then we established a bijection. This is what we did in the last class. So, now today we will show a consequence of this. This was first discovered by Euler, and Euler used it to infer this fact. What is the fact he inferred? It is called Euler's identity. So, k equal to 1 to infinity 1 minus x raised to k equal to 1 plus m equal to 1 to infinity minus 1 raised to m into x raised to omega of m plus x raised to minus omega of m. So, you remember this function I equal to 1 to infinity 1 plus x raised to I. This is the generating function for the sequence representing the number of partitions of n where all parts are distinct. But Euler considers the following functions. So, following product 1 minus x raised to I equal to 1 to infinity. So, instead of plus here he is taking minus, that is the only difference. So, here minus, right. So, what is the, so how does it change? Here you can see that because of the minus sign there will be alternate plus and minus, some plus and minus signs in the terms, right, because there are negative 1 raised to something also. So, how do we decide which terms have negative sign, which terms have positive sign, what will happen to the terms? So, for instance, let us take a general term x raised to n. to the coefficient of this thing, you know, it's again what is contributing to x raised to n is the partitions of n where each parts are unequal, right, because from the first from 1 minus x raised to x raised to 1, right, it will take either take 1x or it will not take an x, but with a negative sign this time, and from this thing from 1 minus x raised to 2, it will either we will not take any 2 or it will take a 2 with or without a minus 1, without the minus, sorry, with minus 1 always, all the time, sorry. So, it will either take or not, right. So, it is also like when I consider the coefficient of x raised to n, its contributions are coming from each partition of n where the parts sum n's are all unequal. But then there is a sign along with each of them. What is the sign? If the number of sum n's were odd, then we will get a negative sign, right. For instance, I can see let us look x raised to 10. So, x raised to 10 can be made by 1 plus 3 plus say 6, yeah, this is fine, right. So, then that means this will be taken to form x raised to n like this. So, we have to get x raised to 1, x raised to 3 and x raised to 6. So, x raised to 1 will come from this, but that is minus x raised to 1. So, then from this thing x raised to this thing x raised to 3 will come, minus x raised to 3 will come, and from 1 minus x raised to 6 this minus x raised to 6 will come, right. So, together this is n is equal to 10, okay. But then we have there are 3 terms, this is minus 1 raised to 3 into x raised to 10 has come, right. It is not just x raised to 10, this is minus 1 raised to 3. 3 corresponds to the number of terms here. If this number of terms was odd, this minus 1 will remain. If the number of terms were even, this minus 1 will disappear because it will become plus 1, right. So, therefore, what matters is in this partition of 10 into distinct parts, how many parts are there, what is the parity of that number of parts. If the parity is odd, then we get minus 1, otherwise we will get plus 1. So, but we have seen that this number of, see, when we consider partitions of a number n where all parts are different, unequal, the number of parts, the number of partitions with even parts and number of partitions with odd parts are equal for most n, right, when n is not of certain form, right. So, that means they will cancel off this minus 1 and plus 1s. So, sometimes you get a minus x raised to 10, sometimes you get a plus x raised to 10, another time we will get a minus x raised to 10, then we will get a plus x raised to 10. But then the number of times we get minus x raised to 10 is equal to the number of times we get plus x raised to 10, because the number of ways we can partition, yeah. So, assuming that n is not of the form, I think n was not of the form omega of minus s or omega of plus s. So, let us take the case of a general n. So, if n was not of this form or this form, we have equal number of partitions of distinct parts where the number of parts is even and number of parts is odd, right. So, therefore, they cancel off. So, they will not even contribute, that x raised to n will not appear because they will have a 0 coefficient with them. So, that will not even come. The only thing which appear are powers of x where n is of this form, omega raised to minus s, omega raised to minus s or omega raised to plus s, x raised to omega of minus s, right. This kind of x's, x raised to the powers of x's only will remain. But then also the coefficients are not at all complicated. We know that the number of even sum n partitions, even the number of partitions with number of parts being equal to even is equal to the number of partitions with number of parts being odd. Sorry, if they are not equal, but just one more, either plus 1 or more 1. But then how will you decide which is more? If it is odd, we should get a negative 1. If it is even is more, then we should get a plus 1. But we know that whether even is more or odd is more is decided by the parity of S. So, we can just infer that it is minus 1 raised to S that will remain. If S was even, the number of partitions contributing to the plus ones will if S was even, the plus ones will be more, 1 more. So, then that S being an even number, minus 1 raised to a 1 number will become minus 1 raised to even number will become a plus 1. But on the other hand, if S was odd, so the number of terms which contributes to a minus x raised to omega of S, right, minus will be 1 more than the ones which is contributing to plus. So, finally, we should have to get minus, but it will come because S is an odd number, minus 1 raised to S. So, that is what will happen here. So, that is why our final expression will look like this when we take the product of I equal to 1 to infinity 1 minus x raised to I. So, what we will get is, initially we will have just 1, that is okay, because x raised to 0 we do not talk about any of the partitions. Then we only have things of the form right, x raised to omega of m and x raised to omega of minus m. Other powers of x will disappear, but the coefficient of x raised to omega of m and x raised to minus omega of m will depend on m, that will be minus 1 raised to m, whether it is even or odd, right, will decide whether we should have a minus 1 here or not. So, m will go from 1 to infinity here. This is what the this is what is Euler's identity, right. So, why do we get this thing? So, we get this thing because this stuff is familiar. What is that? It is actually the inverse of the generating function for the partition number. Remember, the generating function for this function, the main partition function p of 1, p of 2, p of this generating, this is the sequence corresponding to the number of partitions of n, and p of n being the number of partitions of n. This we had found that this is the generating function p of x for this thing is product of I equal to 1 to infinity 1 by 1 minus x raised to I, right, or we can write it as 1 minus x raised to I inverse, right, 1 by 1 minus x raised to I 4. Now, if I take 1 by p raised to p of x, then what will you get? We will get this one, right. So, this is actually the inverse of p of x, right, 1 by p of x is this thing. But we know that 1 by p of x into p of x has to be equal to 1, right. So, there will not be any powers of x on the right hand side when you multiply, right, only 1 will be there. So, we can try to express this way. 1 by p of x is, as we have expressed, that is 1 plus sigma m equal to 1 to infinity minus 1 raised to m x raised to omega of m plus x raised to omega of minus m into p of x. P of x is what? P of x is p of 0 plus p of 1 into x plus p of 2 into x square plus so on. This is what is p of x, right. Now, if you multiply this thing, we have to get 1. So, when we consider the coefficient of x raised to n, so from both sides we can equate the coefficient of x raised to n from LHS and RHS from this thing. What will we get? So, if you do that, because this anyway is not contributing to the coefficient of x raised to n. So, we can, because there are two types of terms for each m we have x raised to omega of m. So, if you want to make an x raised to n, then we have to select from the other part, I mean from this p of x, the x raised to n minus omega, right. So, that means for corresponding to each x raised to omega of m, when we select it from the first part of the product, from the other part we will have to take x raised to n minus omega of m, right. But we know that the coefficient of x raised to n minus omega of m, there will be p of n minus omega of m, right. So, but the coefficient here is just minus 1 raised to m, right. So, we will get minus 1 raised to m into p of n minus omega of m when we make that product. And for x raised to omega of minus m, we have to select from the other part x raised to n minus omega of minus m, and we know that the coefficient for this thing will be p of n minus omega of minus m, right, because the coefficient of x raised to n minus minus omega of m in this sequence, in this generating function, has to be by definition p of n minus p of whatever is the power of x there, that means n minus omega of minus m, right. So, here but the coefficient is just minus 1 raised to m, right, minus 1 raised to m, right. So, therefore, for each m we will have two terms which does not which contributes to the power of x raised to n on the other side, that is minus 1 raised to m into x raised to omega of m plus, sorry, not p of n minus omega of m plus p of n plus omega of m, sorry, p of n minus omega of minus m. These two terms will contribute along with this and this and this and this will be contributing to the x raised to m, and this will happen for each m. So, m equal to 1 to infinity, this will happen, and this will be giving our the coefficient of x raised to n on the other side, but the other side is just 1, right. So, x raised to n has only 0 coefficient there, this has to be equal to 0, right. And sorry, and then there is also one term, this is not true, this is, we have one more term. See, we are finding this into this, right. So, you should note that this one also can contribute to x raised to n. Why? Because it multiplies directly this x raised to n, p of n into x raised to n. So, p of n into x raised to n will come from there. So, therefore, p of n into x raised to n will come from there. So, that is p of n is contributed by that, and for each other term, right. So, for a term like x raised to omega of m will contribute minus 1 raised to m into p of n minus omega of m. A term like x raised to minus or x raised to omega of minus m will contribute, this is minus 1 raised to m into p of n minus omega of minus m, right. So, that together when you multiply we will get x raised to n this way. So, all these contributions are added, therefore, so the final contribution is this p of n plus m equal to 1 to infinity, this thing, this has to be 0. So, now we can take this entire portion to the other side. So, we get p of n is equal to minus of this one, minus 1 raised to m into p of n minus omega of m plus p of n minus omega of minus m. This is what we will get. But then this minus can go inside and then make it plus 1 here, minus 1 raised to m plus 1 into p of n minus. So what is so good about it? So this goes from m equal to 1 to infinity. The good thing about this thing is that we are getting a formula of p of n in terms of smaller p of something which is smaller than n, right. This is a recurrence relation for evaluating p of n. So, but then we will say that there are infinite number of terms here. This is going from 1 to infinity. So, what is good about it at all? But then we can see that this omega of m or omega of minus m, both of them are increasing as m goes bigger and bigger and bigger. So, for a fixed n, so after some time when n becomes reasonably large, this will become n minus some number which is bigger than n, which will give you a p of minus something, and we take p of minus p of something which is when k is less than 0 as 0, right, that we have already mentioned. So, therefore, this things will not give any have any contribution after some time. So, actually it will contribute as long as this omega of m and omega of minus m both remain below n, right, strictly less than n, sorry, less than equal to n, right. Until then only it can contribute. So, after that it will not contribute. So, therefore, it is a finite sum. So, how you will ask how many terms will be there. So, when I put m equal to 1, there will be something n minus we have seen that it is omega of m is 1, right. So, then m equal to 2 we will get something. So, n minus that, and m equal to 2 we will get something. After some time what will happen is, see, when this 3m square minus m by 2 becomes greater than n for some m, then onwards it will we can say that we do not have to consider. This will maybe approximately square root of n values is to be. So, we can estimate exactly what some constant times square root of n values have to be considered. So, there are for each of omega m, omega of minus m, we will have to consider so many values, right. I do not estimate it exactly. So, it is not a very nice recurrence relation in the sense that p of n is being expressed by some 2 or 3 terms which is smaller than n, p of some number which is smaller than n, but we have to consider about square root of n smaller values of n, and then we have to add them together. When I am saying square root of n, some constants are assumed, some constant into square root of n, number of for some number of such values we have to evaluate p and then add them together and minus by the corresponding negative or positive number, positive ones, minus 1 raised to n plus 1 we will have to multiply and add them together, we will get p of n, right. This is good about it. So, of course, this is better than the earlier recurrence relation we have. We so that we can actually find p of n by summing up pk of n's for each k, and for pk we had given some recurrence relation, but you will see that we have to evaluate more values there, right. So, otherwise here we only have to consider about square root of n previous values. This is better. So, this is one consequence of that theorem we have proved. So, this is, so Euler gave this recurrence relation for p of n. Yeah, now that is all we want to discuss about partitions, but then there are more material on this topic. If you want, you can read something more in this book, J.H. Van Lint and R.M. Wilson, A Course in Combinatorics. So, this is the chapter is the 15th chapter. So, chapter 15. So, there are some more material on this if you want to read. So, there will be, of course there will be other books which will give, but this is one reference I can give. But we do not want to discuss more on partitions, because we will want to go to we will want to see other things, right. Now, our the next aim is to look at Catalan numbers. Here also we will have some use for generating functions, but again these Catalan numbers are also quite interesting, because they can capture, or they happen to be the answers for several cute problems. So, if you search in the internet, you can see the listing of problems where Catalan numbers happens to be the answers to the answer for to those problems, right. And you can also see Stanley's book Enumerative Combinatorics for collection of such problems. Now, we let us take some typical problems for where Catalan numbers happen to be the answer. Let us look at this one. Count the number of tree diagrams for rooted ordered binary trees with n vertices. Okay, this is not very common, therefore I will try to explain. So, with one vertex, so we always talk about binary trees. Binary tree means for each vertex it starts from top to bottom, like it is a rooted tree like this. So, like the computer scientists draw, or you could have drawn from below to upward, right. But so we will decide to draw like this, right. So, but every time you may have one child or two children, it can be like this or it can be like this, right, or it can be just like without any children, it can stop. So, this is what the word binary means. It is a rooted tree, because you will be starting from a root and growing downwards. Then we also say that this is an ordered tree, in the sense that you can draw this child, or you can draw say this child. We will consider them as two different trees. These are some diagrams we are drawing. So, this diagram is different from this diagram. This otherwise combinatorially both happens to be the same tree, but in this context we will consider this as two different tree diagrams, right. So, now for instance with one vertex we have just one tree, because it is a single vertex. We will write it as B1 equal to 1. With two vertices we can either draw like this. We start with a root and then we can draw like this, or we can start with the root, we can draw like this. So, either to the left or to the right. So, B of 2 is 2, no, B of 2, B1 sorry, B of 2, B2 is 2. What about B3? So, you can start with the single vertex. First possibility is we can put both the children. So, this is one. Another possibility is you can put a left child, and the next child can be again left of it, or you can put a left child here and then put a right child here. And now you could have given a right child to the root rather than left child, and for the right child you can have a left child or you can have a right child itself. There are 4 different possibilities. I mean, in the usual sense, all these things, all these 4 things are the same tree. It will look like a path on 3 vertices. But when we are talking about this special type of tree diagrams, this order is important. Every time, if whether we draw towards the left or towards the left, the child is put towards the left or towards the right is important. That is different, right? So, therefore, we get 5 different type of things here. So, B3 is equal to 5. So, you can check how much is B4, right. So, see whether it is 14 or not, right. So, that will give you some experience in drawing this thing. So, Next one, so we want to get a general formula for this, namely Bn. So before going further, let us discuss what can be B0. B0 is when there are no vertices. So we can either say it's 0 or 1, but we will decide to say 1 because we want to write a recurrence relation. So we say that there is an empty tree, right. Now this is the recurrence relation we are going to write for this problem. So once you put one vertex, once you add one vertex, now so you are going to draw some tree towards the left. So you are going to draw some tree towards the right. This is the left subtree and this is the right subtree. Now let us say we are trying to get a formula for Bn plus 1 in terms of say Bn minus 1 up to B0, right. This is our aim. Now so once this root is taken, we have n more vertices. Out of the n more vertices, so we can decide to give 0 things here, in which case n things should go here. 0 things are given, then the left tree there is nothing. So we will say that that is B0. So there is a B0 tree, that means there is an empty tree there. For corresponding to each tree possible here, we can see how many trees are possible here. That is essentially Bn by definition. So B0 into Bn possibilities are like this. Now you could have decided to give one vertex here, and one vertex in how many ways you can have. So that is only one way, B1 way, say let us say B1 into, then here it is only n minus 1 vertices. This can be done in Bn minus 1 ways. Now we can try giving 2 here and n minus 2 here. So that will be B2 into Bn minus ways, n minus 2 ways. That means these 2 vertices can be arranged in B2 ways here, and this n minus 2 things can be arranged in Bn minus 2 ways here, right. This is the thing, and like that all the way to Bn into B0. This will be the Bn plus 1. This will be equal to Bn plus 1 equal to B0 into Bn plus B1 into Bn minus 1 plus B2 into Bn minus 1. This is the basic recurrence relation which works here. So with this thing we can try to calculate our B4. B3 we have already calculated. What will be B4? B4 will be B0 into B3 plus B1 into B2 plus B2 into B1 plus B3 into B0. But B0 is 1, B3 is 5, this is B1 is 1 and B2 is 2, right, plus this is 2 into 1, this is 5 into 1. How much is this? So we get 5 plus 5 10 plus 4 14. So like that we can calculate B5, B6 like that, right. Now but our intention is not to compute it this way. So we want a general answer for Bn. What is Bn? So we will use the method of generating functions. So what recurrence relation we have is Bn plus 1 is equal to B0 Bn plus Bn B0. Now let us say this will work for even n equal to 0, right. because B1 is equal to B0 into B0 is what that would mean for when I put n equal to 0. This is correct because this is 1, and then it is just like putting one root and saying that there is an empty tree here, empty tree here. So, total number of trees is 1 into 1. So, therefore, this is correct. So, even for B2 also it will work. B2 is equal to B0 into B1 plus B1 into B0. This is also 1, this is also 1, together it is 2, right, which means that we have put a root. We can decide to make this empty and there is 1 here, or we can decide to put 1 here and make this empty, right. So, therefore, this is true for n greater than equal to 0 till infinity. So, as usual we can multiply by x raised to say multiply by x raised to n plus 1 everywhere, x raised to n plus 1 on both sides, and then sum from n equal to 0 to infinity. So, this will also be summed n equal to 0 to infinity. But then what is this? This is because we are only starting from, because n equal to 0, this is b1, b1 x raised to 1, b2 x raised to 2 and so on. So, this will be just b of x, if b of x is the generating function for this thing. So, let us define b of x equal to sigma n equal to 0 to infinity b n x raised to n. This is, suppose this is the generating function for the sequence b0, b1, b2, b3, etc. So, this will be b of x minus, if you put n equal to 0, so this from b1 on b1 x raised to 1 onwards, x raised to 1 onwards only we have. So, therefore, we have to introduce the b0 into x raised to 0, x raised to 0 is anyway 1, b0, and b0 we have decided to be to 1, to be 1, right, b0 is 1. So, b of x minus 1 is equal to, what is this one, sigma b0 bn into x raised to n plus 1. What we do is, so we will pull out x first. So, this is what we are getting, b of x minus 1 is equal to x into sigma n equal to 0 to infinity. This is your b0 bn plus b1 bn minus 1 plus all the way to bn b0 into x raised to n, if you pull out x, right. And this is actually x into, we can claim that this is b of x square. Why is it so? Because if you consider b of x square, what would be the coefficient of x raised to n in it? To see this thing, you write b of x square as b of x into b of x, and this b of x is actually b0 plus b1 x plus this thing, right, into b0 plus b1 x plus b2 x square and so on. Now, if you pick up the coefficient of x raised to n here, that will be contributed by b0 here, x raised to n should come from here, that is the coefficient is bn, right, and then this will b1 into x, the coefficient will multiply x raised to n minus 1, that is the coefficient of x raised to n minus 1 being bn minus 1, we will get b1 into bn minus 1 and so on, right. So, till bn x raised to n here, bn will be taken and that will be multiplied by b0, this will be the coefficient of x raised to n. So, the coefficient of x raised to n bx in b of x square is actually this, and then we can see that this stuff, see, for n equal to 0 to infinity, this is the way we are writing, that is true for everything. So, therefore, x into b of x square is this. So, again we repeat, we get b of x minus 1 equal to x into b of x square. Now we can rearrange it, we pull it to the other side. So that is x into b of x whole square minus b of x plus 1. Yeah, this minus 1 will become plus 1 on the other side. So that plus 1 equal to 0. Now how will you find b of x? We use the method to solve quadratic equations, because this is b of x is quadratic. So this is b of x square and b of x here and this thing. So we will use minus b, that is plus 1 here, minus 1 will become plus 1 here, plus or minus b square minus 4ac, that is 1 minus 4x by 2x. This is a. This will be the answer to b of x. B of x can be either this or this. So let us see it. So before deciding whether it should be plus or minus here, let us see what is this stuff, 1 minus 4x. This 1 minus 4x root is actually, we know how to deal with this, 1 minus 4x raised to half, right. This will be like 1 plus half choose 1 into minus 4x to the power 1 plus half choose 2 into minus 4x square and so on. So nth term will be what? Nth term will be, so x raised to n's coefficient will be half choose n into minus 4 raised to n, right, minus 4 raised to n. So we have to deal with this nth term now. So that will be like half choose n into minus 4 raised to n, which is this. What is this? This is half into half minus 1 into half minus 2 into half minus n minus 1. Okay, because you started with 1. So the second term is, so we need total n terms. Here there is first term and there are n minus 1 more terms, right, and we have a minus 4 raised to n here, and we, okay, this is divided by n factorial as usual. You have to, if you have forgotten how to do this thing, you have to go back to some classes where we discuss this kind of things and figure out what this was. And now we can see half is here, this can be converted to, say, this is half minus 1, this can be written as minus 1 by 2, right, and this can be written as half minus 2, that can be, that is 1 minus 4 minus 3 by 2, minus 1 by 2 minus 3 by 2. The next will be minus 5 by 2, minus 5 by 2, up to where will we go? This will be 1 minus 2 into n minus 1, right, 1 minus 2n, see, this is 2 n minus 2, right. So this will be minus 2n plus 3, that is minus of 2n minus 3. Okay, this will be minus of 2n minus 3. So everywhere we have a by 2 of case. So those by 2's we can collect. There are n by 2's, so halves, half here, half here, half here, because here there is a half. From here onwards there are n more halves, that will cancel with say one of the 2 raised to n's here. So what we get is, as a result, we will get starting from, see, this is a minus 1 into minus 3 into up to minus of 2n minus 3 here, and we cancel off that So, we will get a minus 2 raised to n left here. We just cancel off this half raised to n with 1 2 raised to n here. So, minus 2 raised to n will remain and an n factorial will remain here. But then there is a minus 1 raised to n here. So, everywhere we have minuses along with everything. So, therefore, that we can, that is there are n minus 1 minus signs. So, they can be collected and we can multiply with minus 1 raised to n here. So, that will cancel off n minus 1 minus 1 and just 1 minus 1 sign will remain. Minus 1 into, we will have a 2 to the power n here, right, and then this is going from 1 to 3 up to 2n minus 3, right, and we have n factorial below. Now, what we can do is we can introduce n factorial. See, what you can see is 1 3 5 7 like this, right, odd numbers only are going. I would like to introduce 2 here, 4 here, 6 here, 8 here and so on up to 2n minus 2 here. That means total of n minus 1 even numbers I want to introduce. So, but this is actually what? This 2 is actually 2 into 1, right? We can write it as 2 into 1. This 4 is 2 into 2. This is 6 is actually 2 into 3. This is 7. This is actually 2 into 4 and so on, right? So, 2's so total 2 into n minus 1. So, n minus 1 2's I need, but then I have this stuff here. So, that I can use up for that purpose. So, we will get minus 1, just 1 2 will remain because n minus 2's I will go for that, give for that purpose, and then that, but I also need to add 1 2 3 up to n minus 1. That means an n minus 1 factorial should be added, that I will have to get below here, n minus 1 factorial. So, to balance this thing, right. So, this I spend off this n minus 1 2's here, 2 to the power n minus 1 as this 2's, and this n minus 1 factorial I am just putting in the denominator. So, therefore, we have above 1 2 3 4 5 6 7 till 2n minus 2, that is 2n minus 2 factorial above, right, and below we have n factorial into n minus 1 factorial, right. So, this we can separate out. So, we can write it as n we can take here and then write an n minus 1 factorial here, because this is familiar. This is what? This is actually minus 2 divided by n into 2n, I will write it as minus 2 divided by n into 2n minus 2 choose n minus 1. This is what it is. So, you can see that 2n minus 2 choose n minus 1 is 2n minus 2 factorial divided by n minus factorial into n minus factorial. This is exactly that term, 2n minus 2 choose n minus 1. So, in principle this is what the coefficient of x raised to n in the expansion of this 1 minus 4x. This is what is the coefficient, this will be the coefficient minus 2 by n into 2n minus 2 choose n minus 1, coefficient of x raised to n. But this is a negative term and it is a coefficient of x raised to n. But then this was not exactly the thing we were trying to do, we were trying to do something more than that. Actually b of x was this. So, we only explored this 1 minus 4x. So, we can try to write this entire thing now. This will look like this. So, we have a 1 by 2x and we have a 1 plus or minus and the rest is 1 plus something. The x raised to n term is minus 2 by n into 2n minus 2 choose n minus 1 into x raised to n and so on. So, if you had selected this plus term here, then you can say that 1 plus 1 2 plus, so minus, so this, then there is this minus terms will remain. So, the x raised to n's coefficient sometime is going to be a negative term. So, that is not allowed because this Bn is some count, it is only a positive integer or maybe the best, the lowest it can become 0, right. So, this is not an option at all, this we can remove. So, we have to take this other option. So, then what happens, 1 and 1 will cancel, this will read as 1 by 2x into 1 minus 1. So, we will get x, right. So, here x coefficient you have to put this thing minus 2 by 1, right, that will look like minus 2 by 1 into 2 into n minus 2 into n minus 2, that means when I put 1 here 2 minus 2 will become 0 and 1 minus 1 will become 0, choose 0 is 1, that will be x, and so on, right, till this term will come, right, minus of minus will become, this minus will go because 1 minus, right, that will all become positive terms now, 2 by n into 2 n minus 2, choose n minus 1 x raised to n, and so on. So, now we can cancel this 2 from everywhere, see every term has a 2 in the this thing, it will go away. Now, this x will go away from the first term, it was x raised to 1, now it will become just 1. So, in the x square term will become x term and x cube term will become x square term and x raised to n term will become x raised to n minus 1 term. So, this will be the, this 1 by n into 2n minus 2, choose n minus 1 will come with x raised to n minus 1 rather than x raised to n, because this x cancelled off 1 x. So, it follows that the coefficient of x raised to n will be 1 by n plus 1, because the next term we have to take 2n, choose n, and this happens to be that Bn. Bn is the coefficient of x raised to n, right, and we will say that this is the nth Catalan number. Let me note once again. So, we started with this recurrence relation b n plus 1 is equal to b 0 b n plus b 1 b n minus 1 plus b n b 0, and noted that our initial conditions are b 0 is equal to 1, b 1 equal to 1 and so on. B 0 is equal to 1 is enough because b 1 we can create from that. For n equal to 1 onwards this recurrence relation works. The generating function is 1 minus 4x by 2x, though we got two solutions when we solved the quadratic equation, it was 1 plus or minus root of 1 minus 4x by 2x, but we saw that if we take 1 plus root of 1 minus 4x by 2x, then all these bi's will become negative numbers. That is not a reasonable thing to do, right, because we are counting something and then we want positive answers. So, positive integers as answers. So, we selected this 1 minus root 1 minus 4x by 2x as the possible solution, and that is the generating function. And now, we evaluated the coefficient of the of x raised to n, it happens to be 1 by n plus 1 into 2n, choose n. This is the nth Catalan number, this is the nth Catalan number, and this was Catalan number. This is called Catalan number because it was first used by Eugene Charles Catalan in 1814 to 1894. He is a Belgian mathematician, and he used it to find the number of balanced parentheses to evaluate an expression of the form x1 into x2 into x3 into xn. We will discuss it a little later. So, that is why it is called Catalan number. And then now we can, for instance, we can see a few examples. Initial values, C0 is 1, do you want to check it? So, right, that should be right, because that is the way we have defined it. Choose n. If you put n equal to 0, this will be 1 by 1 into 0 choose 0, that is 1. So, C 0, I can say C 0 is equal to 1, and C 1, when you put 1, that is 2 choose 1 into 1 by 2 is 1. C 2, that is 4 choose 2, that is 6 by 1 into 3, right, 2 plus 1 is 3, that is 1 by 3 into 6 is 2, and C 3 is what, because this is 6 choose 3, and we have here 1 by 4, this is 1 by 4 into 6 into 5 into 4 divided by 3 factorial, this and this goes and this goes, this is just 5. And again a few more numbers we can calculate. C4 is 14, this and this exactly matches with the values we got for B0, B1, B2, B3, etc. So, that number of tree diagrams, the kind of tree diagrams we are considering, the binary trees, rooted binary trees which are ordered left and right being different, right, the way we draw, actually the corresponds to the Catalan numbers. Nth Catalan number gives the number of diagrams possible when there are n vertices in the tree. Now, our next question is about some sequences. We will see that this Catalan numbers happens to be the answers of several other questions also. At first look it may look different, but we will show that the underlying recurrence relation there is also the same as this. Maybe that is one way of figuring out whether the Catalan number is hiding inside, irrespective of the appearance of the problem. You just try to come up with the recurrence relation. If it happens to be the same recurrence relation as in the previous problem with the same initial conditions, namely the 0th value being 1, then we will, the nth term will be the nth Catalan number. So, we will see some examples which will show how differently things can appear, and then the same Catalan numbers can be the answer for those questions. In the next class, we will consider this.